Hello everybody. The topic of this video is going to be Minkowski spacetime and causality in special relativity. Right. Humans have known space and time as two separate entities since time immemorial. But with the advent of special relativity, the idea of space and time completely changed. Space and time was no longer regarded as two separate entities but as a single entity. The idea of space and time being inextricably entangled was brought about by none other than Einstein's former teacher Hermann Minkowski in 1908. So he regarded space and time. He understood that from the postulates of relativity, special relativity, space and time could no longer be regarded as separate entities, but they are very closely linked, and together he brought out this term space-time, and hence we can rightly call space-time as Minkowski space-time. And in this video we are also going to see how regarding space and time as a single entity changes our views about causality of events. We know that special relativity is consistent with Lorentz transformation equations. Even by going through the Lorentz transformation equations, one can clearly understand that space and time are inextricably entangled. For example, consider two frames of reference. Let me call this as S and this one as S prime. Suppose if S prime is moving at a constant velocity v with respect to the frame of reference S, and then the two in x direction, along the x direction, then we can write a set of transformation equations called as Lorentz transformation equations to understand how a particular point can be transformed from one coordinate system to another coordinate system. So Lorentz transformation equations are useful in transforming a set of coordinates from one frame of reference to another frame of reference. For example, here we know that x prime is equal to x minus vt over 1 minus v squared over c squared. Here we can clearly see that the space coordinate in the frame of reference S prime depends on the space coordinate in S as well as the time coordinate in S. Similarly, we can see that the time coordinate in the S prime frame of reference depends on the time coordinate in S frame as well as the space coordinate in the S frame. Thus, we can clearly see, even based on the Lorentz transformation equations, that space and time are deeply connected, and they are not to be seen as separate entities, but they are to be seen as a single entity. Following Einstein's special theory of relativity, Minkowski realized that space and time are not two separate entities. Therefore, he wanted a convenient way to represent events occurring in space-time. Since space-time is a single entity, we need to conveniently represent events occurring in space-time using what is called as a Minkowski space-time diagram. So Minkowski introduced such space-time diagrams to better understand events occurring in space-time as well as objects moving in such space-time, and to study various dynamical properties of objects moving in space-time. So essentially, space-time is four-dimensional. We live in a three-dimensional space, and normally we use three-dimensional representation of space using coordinates x, y and z. And if you reduce it and represent in two dimensions, one would use x coordinate and a y coordinate. Here, since space is actually space-time and it is four-dimensional, we have three space coordinates and one time coordinate. So in reality, space is four-dimensional. So we have x, y, z as the three spatial coordinates and one temporal coordinate or time coordinate, that is I, C, T. Here we can clearly see that the time coordinate t is multiplied by a complex I and the speed of light c. Why this has to be done will shortly become clear. You can clearly see that if you try to represent this four-dimensional space in two-dimensional notation, we will use one time coordinate and one space coordinate. So the space coordinate here is x and the time coordinate here is ct. For studying most simple problems in special relativity, representation of space-time using two such coordinates is sufficient for most problems. So we see that in Minkowski space-time we have four coordinates x, y, z and I, c, t. In three-dimensional space we have vectors. Something analogical to this we have in Minkowski space-time also, because it is four-dimensional and we use a separate mathematics to deal with it, and that is called four-vector mathematics. Here we have four components of a four-vector. So in three-dimensional space we have three components x, y, z for any vector. Here we will have four components of a four-vector, that is x, y, z and I, c, t as well as a fourth component. And similarly we have here four position, four momentum compared to the position vector here and momentum vector here. In three-dimensional space we have four position, four momentum and so on and so forth. So the entire mathematics that we have to study various physical properties using vector notation, we can transform the whole thing into a four vector notation for studying events and physical properties happening in Minkowski space-time. So the real space-time is actually, the real space is not a single entity, but it is a space-time, a single entity called space-time. Right. Now in a real space, any point in space is going to be represented by three position points. So this represents a point in three-dimensional space x, y, z. So three components represent a point in three-dimensional space. Here similarly we have four components representing any point in the four-dimensional space, and such a point is called as an event. So each point in such a four-dimensional space can be imagined as each point in such a four-dimensional space can be imagined as an event. So various events occur at different points in such a four-dimensional space, and the two events may or may not be having a connection. A causal connection may or may not be there. If there is a causal connection, that is one event impacts another event and there is a causal connection and the event P occurred as a result of event A, then we can say there is a causal connection between event A and event B, and in such a case a line that connects these two events can be called as a world line. Right. Even objects that move in such a space-time, their trajectories can be represented using such a diagram. In its simplest form will have only two coordinates, as I already mentioned, that is one space coordinate and one time coordinate, but in reality you need to extend this to two more dimensions with both y and z coordinates as well. Right. So in a simple representation, to make things very simple, the mathematics very simple, we generally take only x and ct, and such a two-dimensional representation we can draw trajectories of various objects moving in such a space-time. Now we will proceed to discuss further about the motion of objects in such a space-time. Now we will discuss the trajectories of objects moving in space-time. So Minkowski proposed Minkowski diagrams to be used to understand various events occurring in space-time as well as the trajectories of various objects moving in space-time. Let us say an object is moving in such a space-time. With respect to the origin of the coordinate system, we have a curve here, and this curve is called as the world line. So this curve represents the trajectory of an object moving in space-time. And since this curve has various slopes at different points, it indicates that the velocity here is non-uniform, or it is not a constant. That is understanding we can have from such world lines. V is a non-uniform value for this particular object moving in world line, because we know that if you take slope of this particular curve at any point, we say that it is ct over x, and which is equal to ct over v times again t, because the object has a velocity v at that particular instant, then we know that slope is t and t will cancel. So your slope is effectively c over v. Therefore, if you have the slope of a particular world line, then you can get the velocity of the object from this formula, c over slope. So this is how one can clearly get the velocity from the world line of an object in space-time. In the second diagram, you can clearly see that again, with respect to the origin, two world lines are represented. Both of these are world lines, but they are straight lines. Here the world line is a curve, but here the two world lines that are represented are straight lines. This one in green corresponds to the world line of a light beam traveling in the x direction. So from the origin, if the light beam travels at a velocity c in the x direction, its world line will have a slope is equal to 1. So if a light beam is traveling along the positive x direction, its slope is 1. That means it makes an angle 45 degree with respect to the x-axis. Now the second line in red here has a slope greater than 1, and that indicates that this is slope of an object traveling at a uniform velocity. So in this case it was non-uniform because there was a curvature. Here this is uniform velocity v. So this particular world line represents an object with uniform v. Its slope is greater than 1, because here if it is greater than 1, that indicates c is greater than v, which is what is permitted by special relativity. No object can travel with a velocity greater than the velocity of light, and therefore if the object has to travel with a velocity greater than the velocity of light, its slope has to be less than 1, and that line would go to the right of this green line, something like this. This line will have a slope less than 1, and we know that special relativity forbids any real object from traveling at velocities greater than the speed of light, and therefore the slope can never be less than 1 for real objects. So in a Minkowski diagram, all objects will have their trajectories to always the left of the a light beam, world line of a light beam traveling in x direction. To the left, not to the right, because to the right is something that is forbidden by special relativity for real objects, because real objects can never have speed greater than the speed of light. Now we will try to understand Minkowski diagrams in a bit more detail, and we will also try to understand what is light cone. Right. So now in a Minkowski diagram, typically you have two lines with slope 1 and -1, and they are of course intersecting at the origin, and the region bounded by these two lines is a region of possibilities. That means a region where events occur which will have a correlation to the event occurring at the origin. So this origin O is linked to all points lying within this region. So the points below the origin, that is below the x-axis, enclosed by this this triangular region refers to the past events with respect to the event at the origin. And similarly, all the points on the positive axis of CT bounded by these two lines, light beams, these points represent events that are occurring in the future with respect to the event occurring at the origin. So this region is future, so this corresponds to future, and this corresponds to past, and this is the present. Now if the same thing is extended to a three-dimensional space-time, that is two space coordinates and one time coordinate if you take, so if you incorporate y also, x, y and ct, then the same thing which has a triangular shape here becomes a cone here, and such a cone is called as light cone. So for any event one can draw such light cones. So any event that occurs in space-time can have light cones, or each point in the trajectory of the world line of an object can have light cones. Now the significance of this light cone is, again, as I mentioned here, it can be extended here as well. That is, with respect to the origin, all points that lie above this, in this conical region, they refer to future events or the future of an object in whose world line this is a point. And similarly, all the points lying below this line, they are past events of particular with respect to this particular event occurring at the origin. And origin refers to x is equal to 0 and ct is equal to 0. That is what we mean by origin in this case. So outside everywhere is elsewhere. So whatever events occurring elsewhere will have no connection to this particular event occurring at the origin, because all these events do not fall into the light cone of this particular event. So with respect to this, we can say all the other region is elsewhere. So any event that is occurring here will have no connection, causal connection to this particular event occurring at the origin. Same here in both the cases, but just this is only one space and one time dimension we have taken here. Here we have taken two space dimensions x and y, and then one time dimension ct. So this is how one can understand various events occurring in space-time and the connections between various events. Now further we will try to expand this a bit more. For example, an event A is occurring at the origin, and here let us say another event B is occurring, and another C is located, another event C, let us say, is located exactly on the boundary of this light cone, and let's say fourth event D is occurring here. Now how are these four events related to each other, connected to each other causally? That is the whole idea of causality here. We are trying to understand the causal connection between various events using Minkowski space-time diagrams. Right. Now, since this is the light cone of an event occurring at the origin, therefore this is the light cone of event A. And within this light cone, event B is falling, and therefore these two events A and B have a causal connection. So B occurred because of A. If A had not occurred, event A had not occurred, event B would not occur. That is what we mean by causal connection. Here A and C, they are also causally connected. A and C is causally connected, and the speed of light is involved here. We will come to that in more detail later. But what about events A and D? Event D has no causal connection with event A, and therefore irrespective of whether event A occurred or not, D would have occurred, and D has per se no connection with event A. So these two events are not causally connected at all. These kind of causal connections one can understand based on the light cones in Minkowski space-time diagrams. Now let's try to understand the idea of space-time interval, because this is a very important quantity in space-time representation in special relativity to classify space-time intervals into different types. So let us try to first understand in two dimensions. We have, let us say, x and y coordinates, and a point xy in this particular two-dimensional representation of space is at a distance d from the origin. We know that if you do a coordinate transformation, that is, for example, one of the transformation operations is rotation. So if you do a rotation, this is a new set of coordinates x prime and y prime, but this quantity remains unchanged. That is the length of this particular line in this case. So we know that in 2D space, let us say d square is equal to x squared plus y squared is a particular quantity that is invariant under rotation. So this is like a Lorentz transformation also, right? Rotation is like a Lorentz transformation. So we can say that this particular quantity is invariant under Lorentz transformation. One of the operations of rotation is invariant. So we can call this as Lorentz invariant. Similarly, we can see that in space-time also we can have quantities that are Lorentz invariant, right? First, one such quantity one can understand that is invariant is s squared is equal to x squared plus y squared plus z squared minus c squared t squared. Here obviously the minus sign is a result of our choice of coordinates as x, y, z and I, c, t. Now we can understand that why we multiplied ct with an I, because here it goes to minus here, because this quantity is Lorentz invariant. An appropriate choice of coordinates would be ICT. That is the reason why we have a complex I in the selection of coordinates in 4-dimensional space-time. But a more useful quantity similar to this, that is like a distance between two events, but in space-time. That particular quantity is called as space-time interval, and that is defined by del s squared, and that is equal to del x squared plus del y squared plus del z squared minus c squared del t squared. So this particular quantity is a very important quantity in understanding a connection between the causal connection between different events happening in Minkowski space-time, and this particular quantity is called as the space-time interval. And this quantity is Lorentz invariant. So in 4-dimensional space, this quantity is Lorentz invariant, and this quantity is analogous to the length in 2-dimensional space, where d square is equal to x square plus y square is invariant. And another important point is, why do we choose ct instead of just t as the time coordinate? That is because in our 4-dimensional space we need all the coordinates to have same units. We need them to have same units, just like in our real space, 3-dimensional or 2-dimensional space. Each coordinate should have same dimensions of, for example, length. Here also one can have dimensions of length if you choose ct rather than just t. Therefore it is essential that we choose the time coordinate to be ct rather than t, and that is the reason why we have ct here. So the reason for selecting I and c as a factor along with t in 4-dimensional space is now clear based on this minus sign here, as well as the dimensions. Here also it can be meters, here also the units are in meters, or here it is light years, here also it could be light years. That is why we have a choice of ct as the 4th dimension in the space-time. Now we will understand how this particular quantity space-time interval is classified into 3 different types in Minkowski space-time diagrams. Again, let us consider the same situation where we have 4 events: event A occurring at the origin, event B falling within the light cone of event A, event C falling on the boundary of the light cone, and event D falling outside the light cone of event A. Right? Now we know that we have defined already the space-time interval in this particular way, and here interestingly ct is the distance that is travelled by a light beam in time t. right? If you have that understanding, then this classification will be very clear. Suppose if the space-time interval del S squared is less than 0, that would be corresponding to del x squared less than c squared del t squared. We are ignoring the two dimensions here for simplicity. We are taking only one spatial dimension and one time dimension. So we have this. Such a space-time interval is called as time-like interval. What is the physical meaning of time-like interval? Time-like interval of if there is time-like interval between two events, that means these two events have a causal connection. That means there is a frame of reference in which these two events occur at the same point in space, but they are separated by time. That is, they occur at different times. Such events are called time-like events. And event A must be therefore connected to event B, and they are like time. They have a space-time interval which is time-like in this example. Right. The next classification is del square is equal to 0, wherein del x squared becomes equal to c squared del t squared. Such a space-time interval is called light-like. Right. So if two events have space-time interval separation like light-like, then these two events can be connected only by a light beam, or if one travels at the speed of light, then these two events can be seen to occur. So two events that have light-like interval, they are also causally connected, because for in this particular example, event A and event C have a space-time interval which is light-like, and they are connected causally because it is on the boundary. Slightly to the left of this point, a point here left of C would be time-like. A bit this side to the right would be like space-like. That is our third classification, that is del S squared greater than 0, where del x squared will be greater than c squared del t squared, and such a space-time interval is called space-like. That is, these two events, for example, they have no causal connection, their space-time interval is space-like interval. That means event A and D have no causal connection. That is what I mean by space-like. That means there is a frame of reference in which no matter how fast you travel, you cannot be at both those events. That is the understanding one can have for events that are having space-like interval. That is, the separation between the two events cannot be reached even by traveling at the speed of light, so to say. That is the real meaning of space-like interval, and that is why we say that there is no causal connection between event A and event D. So such an understanding one can get based on Minkowski space-time diagrams, and that is why the concept of space-time introduced by Minkowski and the diagrams that he put forward for understanding events and various trajectories of objects is so wonderfully simple. Finally, we will discuss how Minkowski diagrams enable a facile understanding of various relativistic effects, such as, for example, simultaneity. Let us take only simultaneity as an example. How simultaneity can get affected between two frames of reference can be easily understood using Minkowski diagram. Suppose we have two reference frames S and S prime, and we have Minkowski diagrams for a pair of events in both these frames. In the first one, of course, we have x-axis and ct axis, here x prime and ct prime axis. In the first case, we have at the two locations x1 and x2, with respect to the reference frame S, we have two clocks, clock 1 and 2, let us call them, and these two clocks are synchronized, and there is a light source at a point x3 which is exactly midway between x1 and x2, and if two light beams are sent from a light source located at x3 towards x1 and x2, their world lines will be these two green lines, and these two orange lines, vertical lines, they correspond to the world lines of clocks which are at rest at x1 and x2, because for objects at rest in space-time, their positions do not change but time flows. So with respect to the time axis, their world lines have to be parallel. So we have vertical lines in the Minkowski diagrams for objects at rest. Therefore, the world lines of the two clocks are vertical lines, whereas the world lines for the two light beams traveling towards the two clocks x1 and x2 are these two lines, and these two lines reach the two clocks exactly at the same time, which is confirmed by the space-time diagram, where if you extend this, it coincides at at a point t on the CT axis, at a point CT on the CT axis, and therefore we can confirm that these two events are simultaneous with respect to the frame of reference S. Now we know in special relativity that two events that are simultaneous for one inertial observer need not be simultaneous for another inertial observer, of course, who is traveling in a frame of reference which is moving at a velocity v with respect to the first frame of reference. If that is the case, we can say that S prime is moving with a constant velocity with respect to S, and therefore it is another inertial frame in which the same two clocks situated at let us say now x1 prime, x2 prime and x3 prime are the locations now for the two clocks x1 and x1 prime and x2 prime are the locations, whereas for the light beam, the light source rather is situated at x3, midway between x1 prime and x2 prime at x3 prime. Now here the world length for the two clocks will be slanted lines because S prime is moving with respect to S along the x direction with a velocity, constant velocity v, therefore the world lengths in this case will be slanted lines. So we know that any object that moves with a constant velocity in space time will have a straight line for its world line with slope greater than 1. So these two are the world lines corresponding to the clock situated at x1 prime and x2 prime. Now the same two light beams sent towards these two clocks, those two light beams will intersect the two world lines at different points, t1 prime and t2 prime, corresponding to ct1 prime and ct2 prime on the ct prime axis, and thereby confirming that there is a separation in time between these two events in the S prime frame of reference, and therefore we can say that the time difference is which is not equal to 0, whereas in this case the time difference is 0 between the two events. So two events that are simultaneous in S frame is not simultaneous in S prime frame, and this idea of simultaneity getting affected across different inertial observers is clearly easily understood by using Minkowski diagram. We have discussed only simultaneity as an example here. All other relativistic effects can also be discussed, and we can have a facile understanding of various relativistic effects using Minkowski diagrams. Thus, Minkowski diagrams provide a facile understanding of various relativistic effects such as simultaneity, for example, and the causality between various events can also be easily understood using such diagrams. Thank you.